statements are what they're supposed to be. For anybody just joining us, we did kind of have a little bit of a discussion. They are taking their forever quest at the end of class. We're having a work period. Different priorities that kids have include writing down their forevers, studying their forevers for the forever quest, getting some questions answered on the motion module, and then preparing for the actual test with maybe some organizational stuff as well. So here I am in those 3 different ones that we were trying to finish up. First of all, I think we didn't totally finish and fill in the blanks on this guy right here, right? Example number 3 was the first thing that you guys were supposed to finish up. If you didn't notice, hey, can I just teach you like a good academic life lesson real fast? If you're in a huge document, how do you jump to where you want to go without scrolling? Control F. Or I think in a Mac, isn't it like the command button, that little flowery one, the F? Control F, and if I just say, hey, I want example 3. Oh, except my PDF isn't searchable. That's lame. What's the other way that we could do it? You guys don't have page numbers. Man. Maybe I have to download the PDF before I can do that. Let me try it one more time. I thought it'd be searchable, but maybe it's not.
Oh yeah, I tried that too.
Interesting. I'm trying to pull it up, like if I download it, does it now let me see the words? Oh. Yeah, it does, but usually. Wow. Okay, well, it was a good idea for us, huh? If you never knew that trick before, it usually works unless they screenshotted it. Not screenshotted, but it was not loaded as text, which is a bummer. Nice thing is it does go in order, though, so we are going to example 3. Which I believe was right here at the top. So as you guys were looking at example 1, example 2, there's example 3. The solution key, it did have like the worksheet that was blank, and then right after that it said solution. So just in case you didn't find it, here are the final solutions to number 3. Did you guys have any questions with number 3 as far as filling in? Remember I set up the whole thing? As far as filling in the work, we have number 1 with moving to the right because the velocity is positive. I would have said greater than 0. Velocity is decreasing because the velocity's derivative, aka position's second derivative, aka acceleration, is negative. Moving to the left, you guys had to do a sign chart with the critical numbers, which they kind of just show the final answer. They don't show all the work. And then they decide to do like their displacements by just finding the position at the endpoints and the stopping points. And then they just say, how far? 4. How far? 4. But whatever, I don't care, it's down. Total distance just says 4 plus 4 is 8, and 8 plus 20 is 28 for the total distance. Whereas displacement would say, up 4, back 4, you're back to the beginning. And then 20, which would be the positives and the negatives. Any quick questions on example 3?
4, is it just you're plugging into the equation for
position?
Okay.
Because position's the antiderivative. So then the formula itself, hey, forever quiz today, total distance traveled. Total distance traveled is the definite integral from a to b of the absolute value of speed, which is velocity. How do we handle absolute value? Handling absolute value is we start at the beginning bound, we end at the ending bound. We split it up at any of the zeros, which you guys should have already found up here as far as needing to split up your velocity by the stopping points or the resting points, which I think you guys found 1 and 3, right? Okay, so I go up to 1, and then I go from 1 to 3, and then from 3 to 5. We can think about velocity being in the integral, but what that means is, Josh, where am I plugging into again to get these changes in position? The position one, which is exactly the same thing as, hey, forever quiz, the fundamental theorem of calculus says. What does the fundamental theorem of calculus part 1 say? To take the definite integral from a to b of a function little f of x dx. What does that equal? Capital F of, well, you could say capital F of x if you put from A to B, but what does that actually mean? Capital F of B minus F of A. Careful, if this was like on the forever quest, I need you to tell me who capital F is. Where capital F is the what? Close. Where this is this, which means he is who or what? You can say the integral. I was thinking the antiderivative. Or F is the antiderivative. That would be enough to totally ace. Actually, that would be like a long one of stating the whole FTC part 1. That'd be worth 2 points, 20% of the quest. Interesting. So then what I'm saying is, according to FTC, how would we solve? We would just go ahead and say position of 1 minus position of 0. Keep it positive for total distance. For displacement, I would just say, hey, is it positive or negative? I'll keep it. The change in position between that and that, the beginning and the stopping point, the change in position between the middle 2 stopping points, and the change in position between the last 2 stopping points. And how did they organize it? Some of you might like this. They just made a table and said, what's the position at the endpoint, stopping, endpoint, and they just kind of took the differences. Which if it was displacement, plus 4 minus 4, that's 0, plus 20. But they didn't ask for that, they asked for total distance. So a 4 plus absolute value of negative 4, 4 and 4 and 20. Hence the 28 is that total distance traveled. Josh, that good?
Yeah.
Last call on example number 3, considering the motion packet. So then that's 1/3 of what we were supposed to get done. We have another example, worksheet number 3, which is down here, slide number 13. Ooh, I'm at slide number 12. Because you guys didn't have the other one. Bummer. Worksheet number 3. We started, there was the yellow star. I'm sorry, it was slide number 12. I must have deleted one without realizing it. As you guys were doing this, you were checking the relationship between speed and velocity. So to keep my color coding, was I using blue? To keep my color coding, speed says, hey, anything below, I flip up. So one way is to think of it like that. Another way is to actually take the absolute value of every single one. This was one of the easiest ones. Worksheet 3. If you're a little overwhelmed with the motion packet, get to worksheet 3. We're literally just taking our tables and taking the absolute value of those velocities. If we have something positive, we're keeping the same. If we have something negative, we're flipping it to try to think about, hey, this is my speed, and this is my speed. Speeding up happened when velocity was positive and increasing. Speeding up was happening when velocity was negative and decreasing, which sounds confusing, and yet, if I'm going to the left and I'm being pushed to the left, I am going to be sped up. But this one, we see that velocity is negative because all the values are negative in my table and in my chart. Velocity is negative and increasing, which most people would think the speed is increasing, but it's not. It's not. Because the velocity is increasing, as you see, velocity is going up. Acceleration is positive, so what's happening is you're moving to the left, and that acceleration force is pushing against it. Like when you throw a ball. Your velocity is positive, but gravity is saying, no, 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 come here. So the ball slows down, and finally, that initial velocity is overcome, unless you have an engine or something that is not synthetically. Not naturally. What's the opposite of naturally?
Unnatural.
Huh?
Unnatural.
Unnatural. Yeah, unnaturally being maintained. Otherwise, gravity will take over and pull it down. Unless you have wings and lift and things like that. So anyway, this would be an example of, I'm trying to move left, but acceleration is like, no, and so I'm going to be slowing down. Which we can see, not here, because it's like, oh, it's increasing, but when we look at the speed, it's like, oh yeah, of course that speed is decreasing. Look at it go. And then this last one, we have velocity that is positive, so it's staying the same, but we see those speed numbers going down. Velocity is positive and decreasing. Since it's decreasing, the acceleration is negative. That speed will be decreasing. What we're able to put in this final conclusion, you guys have the conclusion page, right?
Yeah.
What we're able to say in the final conclusion is, from that activity, speed was increasing in case 1 and 2. When the speed is increasing, which is in your forever card, for motion, speed increasing, speed decreasing, that always happens when both velocity and acceleration have the same sign. Speed will be decreasing when velocity, remember, v of t, and acceleration, a of t, have opposite signs. They're working against each other, that thing's going to be slowing down. Oh, that was the case. I just literally said what the next statement said. Cases 3 and 4, sorry. So everybody pause for just a second. You guys don't have this in your motion packet because I didn't want you guys to get overwhelmed by it. But I want to see if you guys can answer this question from the forever card, which I'm going to put up here. The motion forever card. The more motion forever card, which for you guys is number 37. Right here, but also right here. So velocity and acceleration have to be working together for something to speed up. Velocity and acceleration have to be working against each other for something to be slowing down. The concept is pretty easy. I'm moving to the left, being pushed to the left, I'm going to speed up. Moving to the right, being pushed to the right, I'm going to speed up. Anything else, I'm going to slow down. So let's see if you can handle it. You ready? If velocity is negative and acceleration is positive, then speed is what? I heard one increasing and one decreasing. Make your case, Hoban.
We both said decrease.
They're what?
We both said decrease.
Oh, I thought Victor said increasing. Okay, then both of you made the case to everybody else because no one else answered. Why decreasing?
Because if velocity is negative, it's under the axis, and acceleration is positive, so it's going up.
Hoban is thinking about the picture because that's what his brain likes the most. So he says that it's below the axis, but the acceleration is moving it up. And so what's going to happen when we look at the speed? It's going to flip up. He's putting it in like one of the cases from the graph. He says, oh, hey, it's below and it's going up, so therefore, yeah, that's one way of thinking about it. Totally works. Speed will be decreasing. The other way is just like, hey, they have opposite signs. Or you're moving left and the acceleration is pushing you to the right, like the ball with gravity example. So definitely decreasing. Different ways of thinking about it. Thanks, Hoban. Number 2, if velocity is positive and speed is decreasing. If velocity is positive and speed is decreasing. If we're going with Hoban's example, velocity is above and getting closer and closer to 0, because whenever your velocities are getting closer and closer to 0, you're slowing down, right? What must acceleration be in order to be bringing that down closer to 0? Victor got it. Negative. Another way of looking at it is this tells me what's going to be true about their signs. Right? Number 3, if velocity is positive and decreasing. If velocity is positive and decreasing. Wasn't that the exact same situation? If you're a graphical person, velocity is positive and decreasing, so it's above the x-axis, but it's decreasing. Then speed is, yeah. Sometimes just finding the right words. If velocity is positive and decreasing, that means acceleration is negative from our increasing, decreasing test. A positive and a negative. It's basically just a restatement of that one up above, right? How about the next one? If speed is increasing and acceleration is negative. Gravity is pulling something down. Acceleration is negative for free fall because of gravity.
Negative.
The velocity is negative because it's like, hey, I'm going down. The speed is increasing and acceleration is negative. Remember, I need, for speeding up, slowing down, to check the signs of the velocity and the acceleration. So as soon as I see increasing, I should think same sign. They have to be working together. Acceleration saying, come on down, and velocity is like, I'm coming. If velocity is negative and increasing, what is speed? If velocity is negative and increasing. Speed is what?
Decreasing.
Which one?
Decreasing.
Decreasing? Okay.
Well, velocity is in the negative axis, and it's getting closer to zero.
And it's getting closer to zero.
That value is decreasing.
So it seems like a lot of you guys like either the visual or just the kind of understanding of velocity is negative, it's down below, but it's increasing. Josh said the key, he says it's getting closer to zero. So speed would also be getting closer to zero. So therefore, yes, speed is decreasing. Another way of looking at it is we could see right here what acceleration is doing. Acceleration is positive, velocity is negative. That's opposite signs. Opposite signs always lead to decreasing. And last but not least, one last way of thinking about it, if a particle is moving to the left and speed is decreasing, then acceleration is careful. Wrong word. Right idea. Moving to the left means velocity has what sign? If speed is decreasing, then they must be having what relationship? Velocity and acceleration? Opposite. So if velocity is negative, what's the opposite of negative? Not increasing. That points me to a derivative, a positive. Acceleration increasing or decreasing is talking about its derivative, the third derivative of position, which is known as jerk, like jerking in a car when your acceleration is moving awkwardly. Good job, guys. That's technically what we were supposed to start class with the motion packet. Even though that wasn't officially in the packet, just to see if you truly understood that idea of speeding up and slowing down. We do have a few of these ideas, quite a few of these ideas in that motion card, which I believe, yeah, in that more motion card, which is for us number 37. I know back in the day it was a different forever, but for us it's 37 because we waited until we did a lot more integration to where we could actually solve things by hand. You have one more thing, right? What was the last one? We've done example 3, we've done worksheet 3, and all we're missing is worksheet 5. There we go. There were a couple things along the way that I don't think I officially assigned. I'm not sure if you guys even had them. Things like the difference between a definite integral and an indefinite integral. Indefinite doesn't have bounds. Gives you an expression for coming back from velocity, good forever knowledge from before. Coming back from velocity gets me to position. I'm going to have a plus c because it's indefinite. Going from A to B, going from time 1 to time 2 is a definite integral. The answer will be a constant because it's going to be a number. The number is going to represent the change in position over change in time. And we already talked about earlier the fundamental theorem of calculus, going backwards. In physics, we would call this plus. Displacement. The answer can be positive or negative depending on whether I am to the right or to the left, whether I am above or I am below my initial starting point or my reference point. In this case, we would say to the right or left because that's what they're measuring. I also have a definite one for my total distance traveled. It will be a number. It'll represent the total distance. So it should always be positive, and I'm always adding up absolute values. But that worksheet that you guys were trying to do is worksheet number 5. So let me pull him up really fast. So sorry about not being able to search it. That's annoying. And here he is. What are you guys going to do if you have geometric shapes and you're trying to do an integral? Semicircle, triangle, triangle. I think I'm talking about area, right, cool kids? So as you were trying to think through 1 and 2 and 3 and then moving on to, I think, was it 4 and 5? And 6. Any questions that you guys want to ask as far as, for those of you that did it, you tried it, you checked it? When the speed is the greatest, thinking about acceleration as the slope, moving to the left, see where the value is above or below, where the signs are opposite or the signs are the same. Anytime they have inequalities, those are sign charts. Total distance, I'm adding areas up. Stick it to the man. Don't you dare simplify. Just write it down and put a big old box around it. They'll be fine. They'll be fine. Do the messy version. Do the messy version. Hey, why is this guy a plus 18, but that guy is a minus 18? What's the difference between the questions in 5 and 6?
Because it's total distance.
Exactly. This guy says total distance. So I think Josh, hold on, you already had it, and then Josh clarified it yesterday. For total distance, what do I do to this big area that should be a negative normally? Thanks, but he's really distracted. Go ahead, Hovan. Do what?
You add it.
I add it. Instead of subtracting something below for total distance traveled, I add it. But when I'm thinking about this guy without absolute value, that'll be the displacement where I would add and then subtract and then add, which you guys can see in the actual packet itself. You guys didn't have number 7, so you didn't have to worry about that because I didn't give it to you. So I guess in that one you were able to save it. This is actually what we're going to be picking up with after the test with the forever card that does come next, but it did not get included for what we are doing as far as integration is net change. Those of you guys that are in the forevers, maybe some of you have been writing them, maybe some of you have been studying them. Does anybody have any questions on the forevers? What something means that you've been studying? We have the definition of the antiderivative, the basic integration rules. Why do all of these have plus C's? What do the integrals not have? Bounds. And so I'm doing an indefinite, so the plus C is there. We have our Riemann sum where I didn't say you had to memorize the whole card, but just know like the different pieces as far as what I might ask you. This one definitely not memorizing the whole card, but I might ask you to fill in either from this backwards. Oh, that's still shifted. From that backwards or this forwards. We already talked about the fundamental theorem of calculus, emphasizing who is capital F. He's the antiderivative. This would be a good whole card with splitting up with absolute value. P.S. If today goes wrong, I'm giving you hints for what else I could ask about the next variation of the quiz. Not just for today, but for future ones. The average value, it's like a rate in that I have a fraction, but I'm coming back, which means an integral. Kind of like average rate, but a little different because I have an integral. FTC part 2 says I'm taking a derivative, special way for doing that. MVT has a C in it with average value and instantaneous value. And then we end right here with more motion. And this is the guy we'll come back to finish off at that motion packet. Any last questions on the motion packet? Any clarifications wanted on the forever cards? Josh.
For FTC part 2, why is it like the derivative, like, is that the derivative of an antiderivative?
Exactly. And those are inverses of each other, which means they cancel out,
Oh,
right?
okay.
Which is why that little f stays little f. But in the midst of that canceling out, I don't want to write on the forever card, so let me do a quick spiffy zoom thing. That wasn't what I intended, but it'll work. There we go. This way I can draw all over it, sorry. Totally. If I was to use the fundamental theorem of calculus part 1, if I knew how to do it, I would technically, like in all of math, do the inside first. Like PEMDAS is, P could be an integral. P is like a grouping symbol, right? So if I were to know the antiderivative, it would be antiderivative of x minus antiderivative of a. That's that FTC part 1. If I go to take the derivative of that, the derivative of the antiderivative leads me right back here. And the derivative of any number, because I don't care, if you plug a constant into a function, you get a number, is going to be 0. And I just end at f of x. But what changes if I'm not talking about that one, and if I'm talking about the other one? Only one thing. I'm not plugging in an x anymore. What am I plugging in? An x squared, or a 5x plus 1, or a sine of x. I'm plugging in something else. So if I knew how to antiderive, when I took the derivative, I would get back to f of u, but what else would you have? You still have your minus 0, and that's why. So it's the idea of, yes, they're inverses, but depending on what gets plugged into an antiderivative that, to be honest, you might have no clue how to find, your answer ends up a little wonky with the u. Does that kind of help?
Yeah.
Anybody else have a forever card question, clarifying question? Okay, I'm off the forevers and I'm off the motion packet, which means I am on to the review and or web assigned questions, etc. I'm on to the review or the practice test. Notes, homework spiral, web assigned questions, etc.